Welcome to the Terminology Leading Practice stream of SNOMED in CT Expo 2020. My name is Yongsheng Gao, and I'm a senior terminologist at SNOMED International. I will be moderating today's session. Please use the QA box to type your questions to the presenter. All questions will be answered at the conclusion of the presentation. I will now pleased to introduce Ronald Cornet from University of Amsterdam. Ronald has been a member of SNOMED committee for many years. Currently, he's a member of the Modeling Advisor Group. As we all know, SNOMED CT represents classes such as diabetes of all kinds, rather than instances such as John Smith's diabetes. It would be interesting to know what instances he will give us in this presentation. Ronald, the name for the presentation is SNOMED for instances. Ronald, please proceed.
Okay, thank you very much for this introduction, Young. It's my pleasure to do this presentation as part of the SNOMED CT Expo 2020. And thanks everybody for attending this presentation. So indeed, as Young pointed out, I'd like to address the use of SNOMED CT as part of a medical record, and especially a medical record in which there is a focus on the use of semantic web standards. So, as was described in the abstract, well, SNOMED has now been delivered as an OWL ontology, which is basically the concept part of representing the world, whereas the individuals part, the data, is being represented as RDF triples, which can be further processed, for example, by reasoning through OWL and querying through SPARQL. And in this presentation, I'd like to address some experience we had and the lessons we learned regarding using SNOMED in this constellation. So throughout this presentation, I'd like to address briefly what OWL is again, what OWL is used for, and especially, of course, in the context of SNOMED CT, how we can work with OWL in representing instance information, and then I will conclude on the lessons we've learned. So first, what's OWL again? And the short answer would be it's the web ontology language. But of course, I'd like to elaborate a bit more on that and look at what OWL and OWL representation means for SNOMED CT. So it is a language, part of the semantic web family of languages and representations that are being provided that enables you to represent knowledge in a, well, rich and complex way. It does provide very many opportunities for representing knowledge, and the OWL profiles provide details or different possibilities of representing more or less expressive ontologies. And then you think about, well, things, so the individuals, but largely it's focusing on groups of things, which we would call concepts in SNOMED, and relationships between things. So the important thing of OWL is that it is a logic-based language. The ontologies provide classes, properties, individuals, and data values, which are stored basically as semantic web documents. And later on, if we look into SNOMED, we will see how that's represented. And one of the distinguishing features is the features of OWL is that it can be used to express complicated and subtle ideas about your data and about the knowledge that you want to define. And the primary uses are basically fast and flexible data modeling and being able to perform automated reasoning. And I'll get to the reasoning later. So it's important to realize that within SNOMED, OWL is represented as a ref set and not as a native OWL file. People digging into this may often ask, okay, so where's the OWL file? And then the maybe disappointing answer would be there isn't, but there is a good reason for not having an OWL file, because it is very easy to create one. And actually representing the OWL knowledge in SNOMED ref set enables versioning, which is something that you can't easily do in OWL alone. And also important, it means that this OWL ref set is part of the release format 2 infrastructure. So it is compatible with all the overall table structures that are being used in SNOMED. And as said, it's very easy to create an OWL file from a versioned RF2 file. So you can basically create an OWL file for practically any release of SNOMED. So as a running example, I'd like to take retinal edema due to diabetes mellitus type 2. And if we look in the release format 2 table, well, we see a couple of things basically saying that this is an active concept, or an active OWL definition, I should say, in the SNOMED CT core model, actually in the OWL axiom reference set. It references retinal edema due to type 2 diabetes mellitus, and then it provides you the OWL definition for retinal edema due to type 2 diabetes mellitus. And I can imagine that, well, you see in bold the OWL expressions being used, like equivalent classes, object intersection of, objects on values from, and then the numbers representing concepts in SNOMED. And I can imagine that this might seem hard to digest, and it's good to look into that a little bit more. Actually, if we look in the way it can be rendered in a more human readable way, here we see the description that the retinal edema due to type 2 diabetes mellitus is, well, object intersection of, which is what we normally would call an and of a complication and some, well, a complication that involves an associated morphology, which is an edema, a finding site, which is a retinal structure, and another role group, which states that it is due to diabetes mellitus type 2. So this is the formal OWL definition for this concept. So we now have these OWL specifications, and what's it for? Short answer, it's for reasoning. And the reasoning, basically, there are 3 important reasoning tasks. The first reasoning task is constructing the taxonomy. So when we define a concept in its stated form, we see that it is being defined as a complication which has an associated morphology of an edema. It relates to a retinal structure, and it is due to diabetes mellitus type 2. And from this definition, we can infer that this condition actually is a retinopathy due to type 2 diabetes mellitus. And we can infer that it is a retinal edema due to diabetes mellitus. So these are inferred parents, if you will, for this concept. So it can be hierarchically classified under those concepts, which was not represented in the stated form. So constructing the taxonomy is one important task. Doing consistency checking is another important task, which is, I think, currently of less relevance for SNOMED CT. It's basically a means for checking if the things that you state about concepts are mutually consistent. And the third reasoning task is the inference on individuals, also called realization. So, for example, if I state that some patient X, has one problem, which is diabetes mellitus type 2, and has another problem that which is retinal edema, I could state, hoping that we have an adequate problem-oriented medical record, that the second problem was due to the first problem. So I state the individual problems, I provide the due to relationship between them, and then you would want to be able to infer that actually this second problem of the patient is a retinal edema due to type 2 diabetes mellitus. And especially interesting, you'd say, okay, I could read that from those two definitions or the two labels and the due to relationship. But it's important to realize that actually this brings in also a different concept identifier. So it says this problem is this long number, rather than just any retinal edema. So we want to be able to also do this reasoning on individuals. And that's what I'd like to focus on in this presentation, how to do modeling, inference, and querying with instances. So it's important to realize that if we work in RDF, basically everything is represented as triples: subject, predicate, object triples, about classes or individuals having some property, which can be an object property or a data type property, and these properties have a value. An object, which can be a class or an individual, like masculine, or a literal, like 1 meter 85. So in this way, we can specify my gender, my body length, and so on and so forth, all as triples. Literals are typed. So in this case, it would be a bit more complex because here it says 1.85 meter, which clearly is a string. And of course, we would want to separate that into some numerical value and a unit. So we could break that up, but for this example, we just take it simply as a literal. And the important thing in RDF is that as much as possible, classes, individuals, and properties are represented using URIs. So for person, I could use the SNOMED URI, and if I click this link, it would be shown in the SNOMED browser. And to identify myself, I could, for example, use this ORCID URI, which points to me from like a research perspective. Well, this modeling, it's important to realize that there's a caveat. If you want to work with, for example, SNOMED's observational entities, that these are specified as classes and not as properties. So if we would look in the OWL specification or the OWL axioms, we would see that gender is a subclass of general clinical state. So it's a class. And length of body is a subclass of body height measure. So again, it's a class. And as we showed previously, the triples, the predicate, requires some kind of property. So you may think, okay, that's probably a mistake, but actually this is a strength because this provides the possibility of explicitly representing all kinds of features. And well, without elaborating too much, for example, you could state that a sitting systolic blood pressure is a systolic blood pressure where the precondition is sitting. And this could, for example, be used to facilitate terminology binding, where we have a user interface representing various elements of, in this case, the blood pressure measurement, whether it was systolic or diastolic, and whether the patient was sitting or lying down. So it's a good thing that these are actually classes and not properties, but it does mean that we have to find a slightly different way to represent the triples. And because gender is a class, it cannot be an object property. So, and I'm referring here to a presentation I previously held as part of the SNOMED research webinars. I there used gender as a predicate. So actually, I've been cheating there. And well, I'd like to make up now for cheating in that presentation. So when we say Ronald has gender masculine, then gender should be an object property, not a class. So how can we, well, that's the one thing, and we'll get to the how shortly after this. But there's another problem that the value for gender, the object, so the value for the object property, that requires an individual and not a class. And masculine is a class in SNOMED. And actually in SNOMED, there are no individuals specified, even though people could argue that, for example, a country like the Netherlands would be an individual. But like masculine is a class in SNOMED. And in an RDF triple, if I want to say Ronald is gender masculine, it should be an individual. So I have to overcome that as well. Now let's look at how we can do that. And I used turtle syntax, one of the popular syntaxes for representing RDF triples, which I hope is sufficiently readable for most of you in the audience. So I can't, and whatever is wrong is made red, I can't say Ronald has SNOMED gender, SNOMED masculine. So I would have to first make sure that I don't do the class masculine, but an individual. And I can do that in quite a simple way by using square brackets and saying it's basically an RDF type, which has the shorthand A. So I can say Ronald SNOMED gender, A SNOMED masculine, an anonymous individual of type masculine. Now I've solved the problem of the object needing to be an individual. Then there's the thing of gender that needs to be fixed. And as gender is a class, I would have to put some property in between to link the individual Ronald to the class SNOMED gender. And I can use a property to link those. For example, I have now used the Semantic Science ontology. Here we've specified the prefix CO for Semantic Science, which has quality relationship. So I can now say Ronald has quality a SNOMED gender. So basically, and then again, whatever is the value for the has quality needs to be an individual. So it's not SNOMED gender, but it's a SNOMED gender. And the ellipses showing I still need to fill in a blank between SNOMED gender and SNOMED masculine. So, and we can do that again using CO, for example, using a property to specify that the individual a masculine is the value, and here we use CO has measurement value to bridge that. And now we have the proper representation to state so that Ronald has gender masculine by making masculine an individual, by making the individual the has measurement value of an individual of type SNOMED gender, which is a quality that Ronald has. So it is definitely more complex than a simple triple, but we see all the elements coming back, Ronald gender masculine, and we fill it up basically with a few brackets and two CO properties, has quality and has measurement value. In this pattern, I've chosen to use anonymous individuals, but there's other patterns that we could apply as well. So if you kind of don't like this one-liner or you have reasons to do it alternatively, you could also name the individuals. And I could, for example, say I create a masculine instance, which I define as an instance of type SNOMED masculine, and I can define Ronald's masculine gender as a SNOMED gender, which has the measurement value a masculine instance. And then, well, I get back to a triple. Ronald has quality Ronald's masculine gender. And this could be especially relevant if we have properties that we or objects that we would want to be able to reuse. So, for example, if you would represent a concept like a leg fracture, it might in some cases be useful to not just say it is a fracture of a leg, so to say, but to make explicit that it's the left leg or the right leg. And of course, as everybody has at most one left leg and one right leg, you can then reuse that instance in other expressions. So you want to prevent ending up, if I would have specified two leg fractures in my record, you would want to be able to distinguish, maybe ultimately even, is this the same fracture we're referring to, and is it the same leg we're referring to? So there can be use cases for naming the individuals rather than keeping them anonymous as we did previously. And there's yet a third pattern. If you really love OWL and you want to use as little individuals as possible, you could say that basically you define a subclass, and then you can say that Ronald is a, and then some instance of a class which has an OWL restriction on property has quality, with some values from gender, which is restricted to the measurement value masculine. Now, interestingly, I actually don't have any individuals at all. I have now subtyped myself as an instance of a class which is defined. So basically, I am, well, someone having a gender which has some value masculine. So basically, we have three patterns for representing that, and they're all slightly more complex than simple triples, but all serve the purpose. Now, we want to use this for doing instance inferencing. So what we want to be able to do, well, if we want to query for everyone having a masculine gender, well, we can do instance inferencing by searching for the CO has quality, some SNOMED gender and has measurement value, some SNOMED masculine. Then the important thing is that whether you use the first, the second, or the third pattern, all instance specifications adhere. And of course, in practice, we know whenever you provide three possibilities, people will use at least those three possibilities and maybe even more. So you need to cater for that. And actually, this is possible. And the good thing is that this way of representing instances and inferencing over instances overcomes the need for having some canonical representation. And I know that in HL7 Fire, for example, there's a lot of discussion on how to, well, uniquely represent certain types of information to prevent having different representations. A drawback, however, is that some reasoners, and I think this goes for SnowRocket, don't support working with individuals and doing the so-called realization. So we have to build an infrastructure, and that's one of the things I would like to talk more on, but I will do in another presentation, to combine OWL reasoners, instance reasoning, and then SPARQL querying. Because in the end, that's what we would like. We'd like to be able to do querying using SPARQL, which is a broadly supported semantic web query language and protocol, enabling the performing queries on triple stores or SPARQL endpoints, as they're called, like BlazeGraph, Virtuoso, or Jena, to just mention a few. As said, well, or I didn't say, but it's important to point out, OWL is not fully supported in SPARQL endpoints. So we need to realize the inferences over the OWL inferences on individuals so that we can query on that to bring together OWL querying and SPARQL, OWL reasoning and SPARQL querying. So that's one of the things that we are currently researching to see how we can further that. And it's important because then, querying for properties of an individual may give different results for different reasoners, and for different, not for different reasoners, but for different representations. So that's yet another topic I'd like to come back to, because all the properties that are not stated explicitly, for example, in my class representation, the third pattern, may be hard to retrieve. So to conclude, the RDF representation of instances can be done. There are various modeling patterns, at least 3, that can be applied. Inference over individuals can be done, but it's not supported by all reasoners. And querying requires the realization of the inference, so doing it also for individuals and storing the inferred axioms. And we definitely need more research and development in this area. And with that, I'd like to thank you for your attention. I'm happy to take any questions, and I hand back to Jan for that.
Thank you, Ronald, for your presentation. Can I ask attendees give us a moment while we switch over from our pre-recorded content so that Ronald can address your questions you have been submitting. Please also note that the session will be available on the event platform for the next 3 months. Hi, welcome back to the live session. I'm Yongsheng Gao from SNOMED International. Firstly, I would like to thank Ronald for a great presentation. It's very highly technical. I think it's a challenge for me, at least, to understand a lot of academic research and understand the difference between the class and the instance. I think first question is about how can we take this research and the investigation you have done into the real practice?
Yeah, thanks for that question, and happy to elaborate on that a little. I think that's actually one of the things where still a lot of work and research has to be done. Also, I think that's actually the area where most of the benefit can be realized. So like I hope I explained, there are the triple stores, and they are capable of dealing with huge amount of triples, like million or billion triples. And we should be able to adequately align those with reasoners that can process the triples against, for example, the SNOMED ontology, but ultimately not just SNOMED, but also SNOMED in combination with OWL representations of other terminologies. And I think that would really enable the possibility of creating like massive reasoning over large databases rather than knowledge bases. And I think also that's actually the area where the true added value of a system like SNOMED will be, if you can really apply it in practice. And in the example I gave on the retinal edema, that you can actually infer that a patient has a certain condition, even though it was not explicitly stated. So those are areas where, well, work needs to be done, but where work is underway, and hopefully we can ultimately get those technologies implemented in electronic health records.
Thanks, Ronald. There's a question from the audience. Waited a long time to hear how instance reasoning would work. It is interesting because SNOMED CT talk about ontology and the classes, how this have been structured. But instance is really the data vital to the clinical practice. So any thought about scaling and performance on the instance data despite the inconsistency between the engines?
Yeah, great question. I think that would be an area also where work needs to be done, and we need to partner with the mathematics and computer science community. Interestingly, I think the SNOMED CT becoming a true description logic ontology has created a large improvement in that area. It was one of the drivers of a lot of research, and I think taking this to the instance level would hopefully again bring the improvements that have been made at a scale with the knowledge bases 15 years ago. Because currently, I think we work with systems like Protégé, where you open a system, you load an ontology, you load some instances, then you do your classification tasks and some querying. But of course, this all should be somewhere out on, well, like database systems like the online triple stores that can communicate against the inference engines. And right now, well, I think the most promising approach is incremental reasoning that, for example, a reasoner like Pellet provides, where you only do the reasoning on the new information provided, the new axioms. So I can imagine that that would be a beneficial approach to combine. But I can imagine if you take a massive electronic health record represented in RDF with a whole bunch of ontologies, that you would need significant compute infrastructure to cater for reasoning over that.
There are other questions we don't have time really. For example, the negation and also the detail about the turtle syntax. I think we have to switch off to the other. And thank you all for participating in the live session, and enjoy your time at the expo.
Okay. Thanks very much.